Welcome to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The unit that I am covering in lecture series is memory segmentation of the subject microprocessor. And today I'll discuss this topic, that is memory segmentation of 8086. This is very important topic of this microprocessor. So let's have an introduction to this topic. So we know that 8086 is having the 20-bit of address bus, and we are not having any 20-bit of registers in 8086. So how we will use the address bus without having the 20-bit of registers? And we have to access all the available memory. So we are having 1 megabyte of memory available in 8086. So how can we discuss it? How can we access it? So let's have a discussion over it. General purpose registers are used as 16 or 8-bit registers. All address registers are also 16-bit. Which are the address registers? Segment registers and stack pointer, base pointer, and your instruction pointer, source index registers, destination index registers. These are all used to contain the offset, to hold the offset. So these are all address registers, and segment registers are used to hold the base addresses of all the segments available in 8086. So these are also used to hold the addresses. So these are the part of address registers. But we know that all these registers are only of 16 bits. So how this 20-bit of address bus can be efficiently used? So segmentation will be used to take care of this situation. A segment is just an area in memory. Total memory size can be considered to be divided into segments of various sizes. Idea of dividing memory is known as the segmentation. So dividing the memory into different segments is known as the segmentation. In memory, data is stored as bytes. Each byte has a specific address. With 20 address lines, the memory that can be addressed is 2 raised to power 20 bytes. That is 1 megabyte. So 8086 can access a physical memory with address ranging from this to this, that is a 20-bit of address. Yes. So basically we are having, since we are having all the 16-bit of address registers, and we have to access the 1 megabyte of memory space, which can be accessed using the 20-bit of address lines. So how is it possible? So we'll have a discussion over it. For this purpose only, we have divided the 8086 memory into segments, that is known as a segmentation. So 20-bit of physical address is to be placed on the address bus to access any location in the memory. So this is the aim, this is the goal. So how will this goal be fulfilled? So for this, the memory as a whole is considered to have different types of segments. These are the segments, each of 64 KB size: data segment, code segment, stack segment, and extra segment. So what is the goal of segmentation? It is used to keep data and code respectively. Code segment contains code only. Data segment is used to store the data. Extra segment is just another type of data segment used in special way. Stack segment is an area in the memory which functions and is accessed from the other 3 segments. So stack is a temporary memory. It can be used as a temporary storage and can be accessed by any other segment. So when we talk about the memory access, so there are 2 types of addressing: linear addressing and segmented addressing. In the linear addressing, the entire memory space is available to the processor in one linear array. In the segmented addressing, the available memory space is divided into chunks. It's called the segments. Such a memory is known as the segmented memory. So these are the 2 types of addressing, how the memory can be addressed. In 8086, the available memory space is 1 megabyte. This memory is divided into a number of logical segments. So these are the logical segments that I have already mentioned. and each segment is 64 KB in size and is addressed by one of the segment registers. Yes. So, segment register, as I have already discussed in the previous lecture, that segment register is holding the upper 16 bits of the base address of any segment, memory segment. The 16-bit contents of the segment register gives starting or the base address of a particular segment, only the upper 16 bits. To address a specific memory location within a segment, we need an offset address. The offset address is also a 16-bit wide address, and it is provided by one of the associated pointers or index registers. So, this is the whole figure which is explaining the memory segmentation. So, this is suppose the extra segment, and it is starting from this memory location. So, here offset address of data, it is held by the DI. So, this is the segment register, and this is the this is a data segment. So, again the DS is storing the address of the segment, that is the data segment, and this is the stack segment register, that is the SS register is holding the base of the stack segment, and stack pointer and base pointer both are used to access the stack, that is to hold the offset address of the stack. Stack pointer basically holds the top of the stack, address of the top of the stack, and the base pointer is used to hold the offset of any random address within the stack. Then we come to the code segment register. It again holds the base address of the base of the code segment, and IP instruction pointer is used to hold the offset of this code segment. So, what is basically the advantages of memory segmentation? That it allows the memory addressing capacity to be 1 megabyte, even though the addresses associated with individual instructions is only 16 bit. So, even if we are having all the addresses of 16 bit, all the registers are of address registers are of 16 bit, then also the 1 megabyte of memory space can be accessed using the 16 bits of address lines. It allows the instruction code, data and stack and portion of the program to be more than 64 KB long by using more than one code, data segment and extra segment. It facilitates the use of separate memory areas for program, data and stack. So, it makes the accessing of all these contents easy. It permits the program or its data to be put in different areas of memory each time the program is executed. That is, the program can be relocated, which is very useful in multi-programming. So, this supports multi-programming also. So, all these advantages can be mentioned for the memory segmentation. So, how will you generate the 20 bit of address using only the 16 bit of address registers? So, to access a specific memory location from any segment, we need 20 bit of physical address. Now, because only by using the 20 bit of address lines, then only the whole memory space can be efficiently used, that can be fully used. So, 8086 generates this address using the contents of segment register and the offset register associated with it. So, these two are very important, that using the segment register and the offset register. We know that code segment register holds the base address of the code segment. The 8086 provides an instruction pointer. So, IP works with code segment here, which holds the 16 bit of address of the next code byte within the code segment. So, instruction pointer holds the offset of the next code, and CS stores the base of the code segment register. So, the value of contained in the IP is referred to an offset. This value must be offset from the segment base address. That is, offset means it should be added to the base segment register, and CS to produce the required 20 bit of physical addresses. So, how this is possible? Suppose the code segment register is having 2000H and instruction pointer is having 1204H. So, this is the condition. So now how will you generate the 20 bit of physical addresses using these two data? So we will shift the contents of code segment register by 4 bits, that is we will make it a 5 bit content. So we will make the 20 bit of contents. So these are the 20 bits of contents in H. Okay, so now we will add the value of IP to this. So adding 1204, it gives 21204. So in this way we are able to formulate the 20 bit of physical address using the 16 bit of address registers. So segment addresses must be stored in segment registers. Offset is derived from the combination of pointer registers, the instruction pointer and immediate values. So the offsets can be the combination of these three, can be the combination of two or the alone also. Let's see an example. So what I have already shown you is that I'll shift this base address by 4 bits to the left, and I'll be able to obtain the content equivalent to 20 bits, and then I'll add the value of IP to it. This is similar to here what is shown. This is the segment address, it will be shifted by 4 bits, and now the offset will be added to this. It will give the 20 bit of physical address. So here suppose code segment is holding this value. So it is being shifted by 4 bits. This is a hexadecimal, so represented by a single digit. Now the value of IP is 4214, so it will be added to this value, it will give 38AB4. So this is the final 20 bit of physical address. Similarly, this is the stack segment register, it is having 5000, and here it is being shifted to left by the 1 digit, that is 4 bits. Stack pointer here, it's having FFE0, it will be added to this, it will give the final stack address. Now again data segment register, it is having 1, 2, 3, 4 the data, and it is shifted to the left. Now the value of DI is added, that is the destination index register is added, which is having the offset. So after adding the offset and the base address, we are able to obtain the 20 bit of physical address. Now each segment is addressed by an address stored in the corresponding segment registers. These are all 16 bit registers, and it stores the base address of the corresponding segment. It's the starting address of the segment. Since segment registers cannot store 20 bits, they store only upper 16 bits. I have already discussed. So least significant nibble is implied to 0. How? 20 bit physical address obtained if there are only 16 bit registers. This I have already explained. This 20 bit address is known as a physical address. It is specified as logical address in the form of two 16 bit numbers in the format base address and offset. So suppose we are talking about CS and IP, we will write like this. If we are talking about the SS and stack pointer and stack segment, and again data segment register and DI. So this is how this the physical address, that is the combination of the two, the logical address and the offset, it is represented like this. So these are all segment registers, base addresses, and these are all offset addresses. So here the example is shown here with the figure. So it is having the base address of 22220H. Offset is 0016 is the offset. So we are at the lowermost byte, the base address is this. So we are shifting this base address by 1 digit, that is 4 zeros. So here we are to obtain 22220H, and by adding offset, that is of 0016H, we are able to obtain the new address. So in this way data segment register is holding this value. So this is the base address by adding zeros on the right, and by adding the offset, 16 bit offset, we are able to obtain the final address. Now when we talk about 20 bit of physical address, so suppose a data byte is stored in the data segment whose base address is this. So I have already explained here in this figure. Then data segment register will contain the number this. The data at any location within this segment is referred to as the offset with respect to the base address. Suppose in this case the offset is 0016H. So now the data, if the data at a location has a logical address is specified by this. So this is the specification, this is the how we write the combination of the logical address and the offset to represent the physical address. Then the number, this is the offset or displacement with respect to the base address. For physical address calculation, the BIU appends the, so this is the role of the BIU, as I have already explained in the previous lecture, that the role of BIU is to append, is to add the segment register content with the 4 binary zeros on the right. Thus the physical address is calculated as this. So this was the content of the segment register. 0 is added to this, and now 4 zeros are appended to on the right to this base address, and then 0016H is added, since this is the offset. So offset is added to the base address, giving it a 20 bit of physical address. Similar is the case with other segments. Offsets are limited to 16 bits, means that the minimum size possible for a segment is only 64 bits KB. So, hence every memory reference by the 8086 will use one of the segment registers, that is DS, ES, SS or CS. It can be any of the segment register. These segment registers are combined to form an offset to determine the physical address being accessed. The figure here highlights that the logical address of the form GS, DS and offset. So let's see what is this. Here code segment register is having this value, since this is the base of the code segment. Then again the data segment register is having this value, so this is the starting address, 16 bits of starting address of the data segment. Again this is the case with extra segment and stack segment. So these are all the base addresses, these are all the segment registers which are holding the 16 bits, that is the upper 16 bits of the base addresses. So what is the role of code segment and instruction pointer? It's the area, code segment is the area of memory where the code alone is stored, and it stores the offset in the instruction pointer, that is a 16-bit registers. Instruction pointer sequences the instructions and points to the next instruction to be executed. If an instruction byte has to be fetched from the memory, the bus interface unit, that is BIU, performs the address calculation using the contents of CS registers and the IP. So we can say that CS and IP works in the combination, that CS is holding the CS register is holding the base address and the IP holds the offset. So 20 bit of physical address is then placed on the address bus and instruction byte is fetched. So this 20 bit of address which has been obtained with the combination of code segment and IP is placed on the address bus, and accordingly the particular code is fetched, particular instruction is fetched. Hence the logical address for an instruction is of the form CS and IP, the combination of logical address and the offset. Similar is the case of stack segment and stack pointer. That stack is any area in the memory, and it is basically the operations performed on the stack and push and pop. It works in the last in first out manner. And there is a 16-bit register called stack pointer which points to the top of the stack, and the base pointer points to any random location within the stack. Its stack segment is like any other segment. Upper 16 bits of its base address is available in the stack segment register. So the stack address of the form, suppose this is the address. So here these are the contents of the stack segment register, and these are the contents of this stack pointer. Yes, the stack pointer and stack segment registers combines and forms the 20 bit of physical address. So in this way, so this is the, suppose that this is the base address is stored in the stack segment. So the 4 zeros are appended at the right, and it forms the 20 bit of content, that is 44660H, and here the offset is added to it. The offset is contained in the stack pointer. So the contents of the stack pointer are added to this address, and it gives us the final address, that is the top of the stack. That's all for today's lecture, and everything which I discussed in this lecture was related to the segmentation, memory segmentation, which is a very special feature of 8086, and it's all and also I discussed all the registers related to the addressing, that is the segment registers, pointers and index registers. So destination index registers, source index registers, all these were the part of all the address registers. And we also studied that how a 20-bit of physical address is obtained by using these 16-bit of registers. So that's all for the day. Thank you.